Okay, so we're on to the final stage of cellular respiration, and I did stress the importance of knowing where each of these stages happen. So let's start with that. This starts, and again, I'm going to pull up this overall cycle. It's called the electron transport chain, sometimes also called the electron transport system. The important part of it is that we're transporting electrons. Okay, and remember, so this little thing here means that anytime we produce those NADHs or FADHs, they were called electron carriers because we know that they can easily undergo redox reactions where we transfer electrons to and from different molecules. They all end up in this final stage electron transport chain. And the final thing to know as well is where this occurs. So remember, we've got the inner mitochondrial membrane here that's outlined in a light blue. This is where the electron transport chain sets up. Okay, so here's the main things that happen during this system. Electrons from the NADH and FADH2s are transported through protein complexes arranged in order of increasing electronegativity along the mitochondrial membrane, the inner mitochondrial membrane. Okay, so each complex is reduced by gaining 2 electrons and then oxidized by losing them to the next complex. So these guys are coming in. I'm just going to try and simplify this for you. These guys are coming in. They're going to give up their electrons in the form of hydrogen. Okay, so see how each of these guys have some hydrogens that they can release. So there's a bunch of proteins. I'm going to show you a picture in a second, but there's a bunch of proteins lined up along the inner mitochondrial membrane, and they're called protein complexes. So what happens is they donate their electron in the form of hydrogen to the complex, and then they take it back. And so it's kind of like a relay race in a way where you are handing off a baton to someone else, and then they hand it off to the next person. So that's kind of the way the electron transport system works. We're actually cycling or filing electrons down a chain of complexes. And so energy is used to pump hydrogen ions into the intermembrane space. And oxygen is the last player to accept the electrons, which also reacts with hydrogen ions in the membrane to make water. So this is a lot to take in, but it's a good summary of what's happening, kind of the overall process. And what we'll do is we'll look at it in a little bit more detail. So protons that accumulate in the intermembrane space create what's called an electrochemical gradient, and I've color-coded these so that we can break this word down and make sense of it. Electro just means we're talking about some sort of electrical charge or electricity, and the electro part of this gradient that we're looking at this term for, it's showing that we have a whole bunch of hydrogen ions in one space together. Hydrogen ions have a positive charge, and when you put a whole bunch of items that have a positive charge near each other, they want to repel. Those are the law of electric charges. Anything with like charges or the same charges, they want to get as far away as possible. So this is what drives this whole process. Another thing that helps drive this process is a high concentration. Remember through the definition of diffusion that we have, anytime we have a high concentration of something in one area, it wants to disperse and spread out to a lower concentration. So everything moves from high concentration to low concentration. So the whole idea behind the electron transport system is that we're forming this electrochemical gradient by putting a whole bunch of positive hydrogen ions in one area, creating a chemical and electrochemical gradient that pushes protons through this complex. So this creates what we call a proton motive force, which moves protons through the ATP synthase complex, driving the formation of ATP. So this complex is really important. This is where we end up getting most of our ATP forming from this last final stage. And what drives this is like a piece of machinery that helps make ATP. And the way that this piece of machinery works is by forcing hydrogen ions through it. And the way that we can get hydrogen ions forced through this complex is by putting a whole bunch in one area, so that we get this repelling happening and we get this desire of a high concentration of something wanting to travel to a low concentration. So it puts pressure and forces some of these hydrogen ions through this complex. And that's what helps drive the formation of ATP. This might be a lot to take in right now without a lot of visual information to go by, but you're going to always be able to come back to this video after you've kind of had the whole complete picture, and that goes for any of these videos. Another term that you're going to sometimes see is this term chemiosmosis. Do you remember that osmosis is really basically just the movement of water to help balance out the concentrations of things? That's what's happening with hydrogen ions, and that's where the chemiosmosis comes from. So osmosis is basically the balance of things by moving water. Chemiosmosis is just referring to the fact that we're moving hydrogen ions in this situation to get the same thing, to get a balance in the end. Okay, I think I have a picture somewhere. Let's see what this is. Okay, so here's an overall picture of it. You're also going to find it in your textbook. Let me just tell you right now. On pages 104 and 105, and it's going to look similar to this. Your textbook actually gives you a lot more information in terms of the names of all of the complexes and a lot more detail about what's going on. And so I'm avoiding that exact picture for now because I just want to use a simple version of this to kind of explain as simply as possible what's happening. So remember the NADHs and the FADHs that we produced all along in any of those stages? They were all transported to this final stage. So you're going to see that what first happens to drive this reaction is that we're removing the hydrogen ion from the NADH or the FADH. These are the complexes that sit on the inner mitochondrial membrane. So if you think about it, this is tough to visualize on this picture here, but let's just say we had the outside of the mitochondria. So here's the outside of the mitochondria. There's a space, right? If you go back to your diagram, we call that the intermembrane space. So between, remember this means between. Here's the inner membrane, and then the matrix would be down below this membrane here. And so this is all happening and lined up on the inner mitochondrial membrane. So this is the outside here. Okay, and so you've got a bunch of protein complexes lined up along the inner mitochondrial membrane that are going to do two things basically. The hydrogen comes off of NADH. Okay, and if you think of what hydrogen has one electron and has one proton. It donates its one electron to the complex, which leaves you with a positively charged hydrogen, right? You're just left with a proton, so it has a positive charge of 1, which is where the hydrogen ion comes from. Some of the hydrogen ions stay on the mitochondrial matrix side of things, but some are also pumped through these protein complexes. That's also part of their job. So some hydrogen ions are getting pumped over to the intermembrane space. And the electron that was released gets passed on, and then it gets passed on to the next one. So remember, like a relay race, it's passing its electron on to the next complex, and this is just continuing. So we're adding electrons into this relay race through NADH and through FADH. So the same thing's happening here. So those electrons get pumped over, and some hydrogen ions are here. Some of those get pumped through to the other side. And the important thing here to remember is that what we end up with in the intermembrane space is a really high concentration of hydrogen ions relative to this side. So we end up with a higher concentration on this side. We have a bunch of positive charges near each other, so they want to get as far apart as possible. We also have a high concentration of a substance which wants to migrate to somewhere with a lower concentration, and that's what forces this process here. So this is an ATPase, sometimes called ATP synthase, and it's basically like a piece of machinery that is designed to pump hydrogen ions back through. Okay, and in the process of pumping hydrogen ions back through, it's also driving the production of ATP from our ADP. Okay, so this is a really, really important process of making a whole bunch of ATP, this ATP synthase complex. And what makes this run is the production of hydrogen ions that want to push through it. And why do these want to push through it? Because there's a high concentration of positive charges near each other, they want to get away, and because there's a high chemical concentration of something here that's wanting to push away. And that drives these through the ATP synthase, and Anytime you're driving hydrogen ions through ATP synthase, you're creating ATP in the process. So this is how a lot of ATP is formed in the overall process of cellular respiration. Now you might also be asking yourself what happens in the overall process. If you recall the other product that we're producing during cellular respiration, we produce carbon dioxide. But if you remember, that equation also told us that we produce water as well. Here's where the water gets produced. So those electrons were passed along the protein complexes. They end up on this side of the membrane, so in the matrix. And remember, there's still some hydrogen ions floating around here. And so in order to make water, we need hydrogen and we need oxygen. And so 2 free hydrogen ions, remember these are just the protons, and 2 electrons that are exiting this complex come back together to make just hydrogen, neutral hydrogen, right? 1 proton plus 1 electron. And they come together with oxygen to form our molecule of water. Okay, and so for every for every one time the electrons come through, one pass through of this, we end up with 2 molecules of hydrogen. 2 molecules of water. And you'll see in our summary as well that how many ATP are formed during this process as well. So now that we've reached the end of stage 4, one important thing that I'm going to have you go back and do is just sort of summarize, where does all of our ATP come from? So what is the net gain of ATP during each of these stages, and during what processes do we get the most, the least, and sort of take some time to kind of connect back and see the whole flow of this process, and it might start to make a little bit more sense now that you know the final stage and what some of these key players, important players, are in this stage.